So in this last video, what we're going to do is we're just going to take a look at being able to evaluate the limits of these vector value functions. Most of the time, we're not going to get a real number. What we're going to do is we're going to end up getting a vector, which makes sense because that's what a vector value function is. So it's not what number does this approach, but what vector does this approach as t approaches a specific value. All right. What we're going to do is we're just going to take the limit of each of the coefficients of I, j, k respectively, and then we're going to finish up by putting it as a vector. All right, so here's what we're going to do. We're going to rewrite this. We're going to say lim as t approaches 0 of t, which is the first coefficient, lim as t approaches 0 of ln t plus 1 divided by t, and then I'm going to leave a little space, and then we're going to have lim as t approaches 0 of 1 minus cos t divided by t. Right, notice we left the I, j, and k off. We'll worry about that in a few moments. Now, let's think back to Calculus 1. How do we evaluate a limit? Well, first thing we do is we try direct substitution. And if we get a value that's in the domain, then we just go through and we substitute. All right, so by direct substitution, we get 0. All right, that's okay. That's a good value. For the second one, by direct substitution, we get ln of 1, 0 plus 1, which is 0, and we get 0 over 0. All right, now, you may remember from Calculus 1 that this is one of those special types of cases of an indeterminate form. And remember, when you have an indeterminate form, you use L'Hopital's rule. And L'Hopital's rule basically says you're going to take the derivative of the top, the derivative of the bottom. You're not going to use the quotient rule. And then you're going to evaluate from there. So what I always do to denote that I'm using L'Hopital's rule is I put an L in a circle. I've seen that before in a few textbooks. It makes it really nice and easy to understand how you got from one step to the next. All right, so we're going to find the derivative of the top. So now we have to go back to Calculus 1 and think a little bit. Derivative of ln t plus 1. Well, derivative of ln is 1 over whatever's inside the parentheses. So 1 over t plus 1. And then the derivative of t is going to be 1. In fact, let me erase this mess so I can make this look a little bit better. And there should be a limit in here, so I'm going to try to squeeze in lim as t approaches 0. Right. Now we're going to try direct substitution again, and this time we're going to get 1 over 0 plus 1 over 1, which is 1. All right. So remember that trick from Calculus 1. If you end up with one of the indeterminate forms, just use L'Hopital's rule. All right. The other component that we have to try to find the limit of, we have lim as t approaches 0 of 1 minus cos t divided by t. If we try direct substitution, we get 1 minus 1 over 0, since cosine of 0 is 1. And that's going to be 0 over 0 again. So what that means is we can use L'Hopital's rule. We can take the derivative of the top. So now we get lim as t approaches 0. The derivative of 1, and I'm going to do this really slow for the first few times because maybe you haven't done some calculus in a while. Derivative of 1 is 0. Derivative of negative cos is negative or positive sine. So we have minus a minus sine t. And derivative of t on the bottom is 1. We try direct substitution. That gives us sine of 0 over 1. Sine of 0 is 0. Right? So what we have is we have 0 for the I component, we have 1 for the j component, and we have 0 for the k component as our limits. So the limit as t approaches 0 of our function r of t is going to be 0i plus 1j plus 0k, or in other words, that's just j. So that's how we're going to find our limits. All right. A second example of this, just to reinforce, but this time we're approaching infinity. All right, so we have e to the minus t, t squared minus 1 over 2t squared plus 1, and then t over t squared plus 1. So let's find the limit of each. So this is lim as t approaches infinity of e to the minus t. We could rewrite this as lim as t approaches infinity 1 over e to the t. Right, if that helps for you to remember how to take the limit of that. Now we know that this just theoretically becomes 1 over infinity. All right, and that's not correct to write it, but just think of that as 1 over infinity, which means we're going to end up with 0. Right. Now we have lim as t approaches infinity of t squared minus 1 divided by 2t squared plus 1. If we try to substitute infinity, and I know that's not a good word to say substitute infinity, but as t approaches infinity, we get infinity squared minus 1 on top, which is infinity, 2 infinity squared plus 1 on the bottom, which approaches infinity as well. So once again, we end up with one of these L'Hopital rules. Okay. So if we do that, lim as t approaches infinity, the derivative of the top, 2t minus 0, the derivative of the bottom, 4t plus 0. All right, remember the derivative of a constant is always 0. Derivative of a polynomial, take the exponent, move it in front, and then subtract 1 from the exponent. This just becomes 1/2. Since the t's would cancel out, 2 over 4, there's nothing to substitute. So we end up with 1/2. Right? So that's going to be for the j component. Remember, 0 is for the I component. And then finally, we have this t over t squared plus 1. Again, if we try to approach infinity, we get infinity over infinity. And that means we can use L'Hopital's rule. So now we're going to end up with the limit as t approaches infinity. The derivative of t on the top is 1. The derivative of t squared is going to be 2t. The derivative of 1 is 0. So we get 1 over 2t, and we can think of that as 1 over infinity. And even though that's not correct, that's how we're thinking of it, which just becomes 0. All right. So after all of that, the limit as t approaches infinity of our function r of t is going to be 0i plus 1/2 j plus 0k, or just 1/2 j. Right. So hopefully this is a good overview as to how to go through and evaluate the limits of these vector value functions. In the next series of videos, we're going to be taking a look at derivatives and integrals of vector value functions.